Hello, this video is about fluid mechanics. In fluid mechanics, there is a quantity called pressure, in which pressure P is defined as force over area, and the unit of pressure equals to Newton over meter squared, which is also called Pascal. Pressure is a scalar quantity, and for example, let's say there is a cube with surface area A. And if the pressure at the top of the cube equals to P1 and pressure at the bottom of the cube equals P2, then the force along the z direction, if this is the z-axis, equals to P2 times A minus P1 times A, because P2 times A is going to exert a force along the positive z direction, and P1 times A is going to exert a force along the negative z direction. There is also pressure from the atmosphere, in which P atmosphere has a numerical value of approximately 1.01 times 10 to the 5th Pascal. So for instance, if there is a cylinder, a gas cylinder, which is covered by a piston of mass m, then the pressure inside the cylinder equals to P atmosphere plus mg divided by A, where A is the surface area of this piston. The reason that the pressure inside the cylinder has this form is because both the atmospheric pressure and the weight of this piston is pressing downward. Therefore, these two pressure will add up. So let's say there is a water in this cup, and if I take an infinitesimal mass such that the dimension of this mass is delta x, delta y, and delta z. Drawing the force diagram, there is the weight mg that is exerted along the z direction. But since this fluid is under static equilibrium, the sum of all the forces must add up to 0. Therefore, the sum of the forces in the x direction, sum of the forces in the y direction, and the sum of the forces in the z direction must add up to 0. Because sum of the forces in the x direction must add up to 0, this means that pressure at position x0, if this position is x0, must equal to pressure at position x0 plus delta x, because if the pressure on two different sides are different, then there is going to be a net force along the x direction, which should not occur in a static equilibrium condition. And this means that change in pressure along the x direction equal to 0. Using the same logic, the change in pressure along the y direction must be 0 because there should be no net horizontal forces. The sum in the force along the z direction must be also 0, which means the weight mg must equal to pressure of position z0 times area minus pressure of z0 plus delta z times area. And if I divide this expression with the volume of this mass, I get mass over volume times gravitational acceleration equals to P of z0 times area over volume minus P of z0 plus delta z times area over volume. Mass times volume, this becomes the density of water, which is denoted as rho. Area over volume is simply 1 over delta z, because in this case the cross-sectional area is A, and A times delta z equals to the volume of this cube. So rewriting this expression, rho g equals to P of z0 minus P of z0 minus delta z over delta z, which equals to minus change in pressure along the z direction divided by change in z. Therefore, we can conclude that the derivative of pressure along the z direction equals to negative rho times g. Now, if I want to get a pressure inside this water, point P, where the height from the surface equals to h, if I set z as the downward direction, then dp dz is just going to be rho g, because previously I set the z-axis as the upward direction. Therefore, P at position z is going to be integral from 0 to h of rho g dz plus P of 0. And P of 0, or pressure at the surface, equals to P atmosphere. Therefore, the pressure at height z equals to P atmosphere plus rho gz, and therefore the pressure at this point would equal to P atm plus rho gh. There is also a quantity called the gauge pressure, in which the gauge pressure is defined by pressure subtracted by the atmospheric pressure, in which for the case of the water, this would equal to rho gh. There is a device called the barometer, in which this device looks something like this. So inside this device, it is filled with water, and this is a vacuum space. If I call this height h, and call this point 1, call this point 2, then pressure at 1 equals to pressure at 2, because change in pressure along the horizontal direction must equal to 0. But pressure at point 1 equals to the atmospheric pressure, and pressure at point 2 equals to rho gh, because in here, since this area is vacuum, there is no atmospheric pressure. So therefore, the measured atmospheric pressure equals rho gh, where rho is the density of the fluid and h is the measured height of this fluid. Now, for water, the height would be P atmosphere divided by rho times g, which is approximately 10 to the 5th power Pascal divided by 1,000 kilograms per meter cubed times 10 meter per second squared, where I'm approximating g as 10 meter per second squared and the atmospheric pressure as 10 to the 5th power Pascal. And this would lead to the height of 10 meters, which is extremely high. That is why we use a substance called mercury, where the density of mercury is far greater than density of water. And the height from mercury is roughly 760 millimeter. And this is why we note the pressure of the atmosphere as 760 millimeter mercury, because this means that the atmospheric pressure is equivalent to the pressure from 760 millimeter of mercury stacked on top of each other. There is a device called the U-tube, which is a U-shaped tube. And for instance, if the U-tube is partially filled with water and partially filled with oil, if I call this point 1 and call this point 2, call this height h2 and call this height h1, then pressure at point 1 equals to pressure at point 2. And this is because change in pressure along the horizontal direction is equal to 0. The gauge pressure at point 1 equals to density of oil times g times h1, and the gauge pressure at point 2 equals to density of water times the gravitational acceleration times h2. And therefore, rho oil times g times h1 equals to rho water times g times h2. Canceling out the gravitational acceleration, rho of oil times h1 equals to rho of water times h2, in which we can calculate the density of oil by multiplying density of water by h2 divided by h1. So let's say there is water inside this U-tube such that the height at both points are the same. And if the force is applied at the right-hand side such that the right side is going to be depressed and the left hand is elevated by distance x, change in pressure between the 2 points equals to rho g times 2x, because the total difference in height is 2x. Then the force that is applied from the water equals to negative 2 rho gx times area, because this term is the pressure, that term is the area, and there is the negative sign because the force will be applied to reduce the distance of x. Since F equals ma from Newton's law, negative 2 rho Ga times x equals ma, which solving for a which equals to d2x over dt squared equals to negative 2 rho Ga over m times x. And if I call this whole quantity as omega squared, d2x over dt squared equals to negative omega squared x, in which this was the equation for simple harmonic motion. Therefore, x of t, which is height of this water oscillating, can be written as a form of x naught times cosine of omega t plus some angle phi. Let's say there is a U-tube that looks like this, where the area at the left side has A1, area on the right side has A2, and this U tube is filled with some incompressible fluid, let's say water. If force of F1 is applied, then this force is going to cause the right hand side to be lifted with force F2. But pressure at point 1 must equal to pressure at point 2 because the change in pressure along the horizontal direction must be 0. This means F1 over A1 must equal to F2 over A2. And if U tube is generated such that A2 is far greater than A1, then F2, which is the outputted force, is going to be far greater than F1, which is the inputted force. This means that using such device, one can generate a great amount of force which can be used to lift a heavy object. But energy is conserved in this case. Work done by force 1 equals to F1 times some distance x1. And this equals to pressure at point 1 times area A1 times delta x1, which is pressure at point 1 times change in volume, in which I'm going to call it delta V1. Work done by force 2 equals to negative F2 times delta x because this point received work, and this equals to pressure at point 2 times area at point 2 times delta x2, which equals to pressure at point 2 times change in volume at point 2. But change in V1 must equal to change in V2 because this fluid is an incompressible fluid. Therefore, change in volume at this point must equal to change in volume at that point. Now, because the pressure at point 1 equals the pressure at point 2, the work done by force 1 cancels out the work done by force 2. Therefore, energy is conserved. The Archimedes principle is the most important fact to remember in fluid statics, in which this principle states that the buoyancy force equals to the weight of the water displaced. So let's say there is an object with surface area A and submerged height of h that floats on water. Since this object is floating, the net force must equal to 0, which means the weight mg must equal to the force that is exerted from the water, in which I'm going to denote it as the buoyancy force. Pressure at the top of this object equals to P atmosphere, since there is no other fluid on top. And pressure at the bottom of this object equals to P atmosphere plus rho gh, which means change in pressure equals to rho gh, and therefore the net force must equal to rho times g times h times the surface area. Now h times a, this equals to the volume of the water that has been displaced, and therefore buoyancy force equals to rho times volume of displaced water times g, which is mass of the water times gravitational acceleration. Therefore, the mass of the object times gravitational acceleration must equal to mass of the displaced water times gravitational acceleration. And canceling off these terms, the mass of the object must equal to mass of the displaced water, in which this is a consequence of Archimedes' principle. The next part is fluid dynamics, in which, in this case, the net force is not necessarily 0. And so far, I don't think there was a question in the F equals MA asking about fluid dynamics, but just in case, I'm going to go over this topic. And the major equation in fluid dynamics is called the Bernoulli's equation. So let's say there is a tube that looks like this, and at this point there is a pressure of P1, height h1, and at this point there is pressure P2 and h2. Bernoulli stated that P1 plus rho g h1 plus 1/2 rho v1 squared, where v1 is the velocity of the fluid traveling at point 1, equals to P2 times rho g h2 plus 1/2 rho v2 squared, where v2 is the velocity of the fluid exiting this cylinder. An example of this is the airplane wing. On the top of the wing, the air has to travel a greater distance than the air at the bottom of the wing, which means velocity at the top of the wing is much higher. And since velocity is higher, the pressure is going to get lower. Since the pressure at the top is lower than the pressure at the bottom, there is going to be a net force that lifts the airplane upward, and this is why airplane floats. Another example is perfume. Let's say this is a simplified diagram of a perfume. If you press the perfume, then the air is going to travel at some velocity v. And since this velocity is higher than the velocity inside this perfume bottle, the pressure at the top is going to be lower than the pressure in the inside, in which, similar to like an airplane, the perfume is going to lift it up, and that is why if you spray the perfume, perfume exits through the hole. So I've prepared some questions related to fluid mechanics. And similar to kinematics, there aren't that many questions related on fluid for the F equals MA exam. There's going to be probably one or maximum of 2 per year. So the first question is from 2016 question 2. So in this question, inside a container there is water at the bottom of a layer of an oil. And an object is floating such that 1/3 of its length is submerged in water, the other third is submerged in oil, and the rest of the third is floating on top of the surface. Then if additional oil has been added and the object is fully submerged in the oil, then the question is asking what fraction of this object is submerged in oil. And using the Archimedes principle for the first situation, mg, the weight of this object, must equal to rho oil times L/3 times area times g, plus rho water times L/3 times area times g, because this is the volume displaced of oil, that is volume displaced by water, and multiplying by respective density would result to their masses. Canceling out the gravitational acceleration, I get m equals to rho oil times L/3 times a, plus rho water times L/3 times a. Since rho oil equals to 800 kilogram per meter cube and rho water equals 1000 kilogram per meter cube, this equals to 800/3 times L times A plus 1000/3 times L times A, which is 1800/3 times L times A, which equals to 600 times L times A. Now, for sake of simplicity, I've left out the units, in which there should be an additional unit for density. Using Archimedes' principle of the second situation, mg should equal to rho oil times x times a times g. Again, canceling out the g, m equals to 800 times x times a. But since m equals to 600 L times a, 600 times L times a equals to 800 times x times a, in which, solving for x equals to 3/4 of L. Therefore, 3/4 of the object would be submerged in oil. And thus, looking at the answer choice, B would be the correct answer. And the next question is from 2017 F equals MA, question 9. In this question, there are 3 cylinders with same base area, but they have different shapes. And if equal volume of water is poured into each cylinder, then height at cylinder A is going to be greater than height at cylinder B, and height at cylinder C is going to be greater than height at cylinder A. Therefore, height at cylinder C is going to be greater than height at cylinder A, which is greater than height at cylinder B. Now remember in fluid statics that pressure as a function of height equals to the atmospheric pressure plus rho g z, in which if z increases, then the pressure increases. Therefore, we can claim that pressure is going to increase as height of the water increases, which means pressure of container C is going to be greater than pressure at container A, which is greater than pressure at container B. And the question is asking what is the inequalities relationship between the forces that are applied at cylinder A, B, and C. But since the base area is the same, force, which is defined by pressure times area, is going to be proportional to the respective pressures of the cylinder, in which therefore force that is exerted on cylinder C is greater than force that is exerted on cylinder A, which is greater than force on cylinder B. And thus, in this case, D would be the correct option. And the next question is question 10 from the same year. In this question, there is a plug that is stuck on the handle of the milk jug, in which through this handle there is a milk with height small h. And on the other side of this jug, the height of the milk is big H. Now, because of this plug, the pressure inside here is not necessarily atmospheric pressure. But since this part of the jug is open, pressure at the surface of this milk here equals to the atmospheric pressure. And therefore, pressure at the bottom is simply P atmosphere plus rho G big H, because the distance here is big H, and from fluid statics, this is the form of pressure as a function of height. Which means the gauge pressure, which is defined as pressure minus the atmospheric pressure, is simply rho G times big H. And from the answer choice, this corresponds to answer choice B. The next question is question 22 from 2018 AF equals MA exam. In this problem, there is a rectangular boat in which at the bottom there is a hole. So therefore, water would leak in through this hole. And the question is asking which of the following graph represents the height difference between the water level and the water level inside the boat as a function of time. Let's say the initial height difference equals to h. And after some time has passed, a water level of delta h has built into this rectangular boat. Then the new height difference equals to h minus delta h. And from Archimedes' principle, the buoyancy force is going to be proportional to h minus delta h. And note that this buoyancy force, the new buoyancy force, is less than the original buoyancy force where this water level was absent, because the original buoyancy force was proportional to h instead of h minus h. And therefore, since the net force is going to point downward, the boat is going to descend by a level delta h to establish a constant height difference of h. Therefore, height as a function of time would just be constant. And looking at the options, A best represents our calculation. And the final question is from 2018B, question 10. Now, before solving this question, I would like to mention that volume of air is inversely proportional to the pressure of air as long as temperature is constant. In this problem, there is a balloon submerged at height h and the same exact balloon that is submerged at height 2h. And the buoyancy force of the first balloon equals to B naught, and the force of the second balloon equals to B. From Archimedes' principle, the buoyancy force is proportional to the volume that is occupied by this balloon, and this volume is inversely proportional to the pressure. And remember from fluid statics that pressure at height h in water equals to the atmospheric pressure plus rho g h. And therefore, the buoyancy force is inversely proportional to PATM plus rho gh. Similarly, for the second balloon, force of buoyancy is proportional to volume, in which this is inversely proportional to pressure, which equals to 1 over the atmospheric pressure times 2 rho gh, because in this case, height equals to 2h. And note that this fraction is smaller than 1 over P atmosphere times rho gh, in which B is going to be smaller than B naught. And this answer choice corresponds to D.